Good morning. In today's session, we are supposed to study about the operational amplifier. If you see the various branches of the electronics which we have, industrial electronics, instrumentation, communication, power electronics, all there, we are using the amplifier. So we are using the various electronic circuits which we can use in the applications like amplifier, waveform generator, timer, various arithmetic circuits. You can use adder, subtractor, multiplier, any type of the amplifier. So here we are supposed to study about the op-amp. What is meant by op-amp? One electronic device which we can use to construct all the circuit mentioned above. It means what? We are supposed to construct the circuit like timer, waveform generator, arithmetic circuit. At that time, if we are having the one electronic device which we can use to construct all these circuits, at that time we can call that device, that amplifier, as a operational amplifier. So here we are using the amplifier. Voltage amplifier will consist of transistor which will have many other components like it will have bypass capacitor, biasing resistor, coupling capacitor. It means we can make voltage amplifier by using the transistor, capacitors and the resistors. So here, in order to get the higher voltage gain, we have to use more than one such amplifier together. This will make the circuit bulky. It means what? It will get higher amount of weight because here we are supposed to increase the gain. For that, we are using the more than one amplifier. So it will make that circuit bulky. So here, instead of these, people are using the amplifier that will be in the form of integrated circuit. Instead of transistor, instead of this capacitor, bypass, biasing capacitor, biasing resistor, we are supposed to use amplifier that will be in the form of IC. So here we are supposed to study why we are calling operational amplifier. We are calling amplifier as the op-amp because it will configure to perform variety of operations. It is doing lots of applications at a time. How it can be used as amplification, we can do addition, we can do subtraction, we can use amplifier as a differentiation amplifier, we can use amplifier as an integrator. It means what? We can do variety of operations like amplification, addition, subtraction, differentiation, integration by using a single IC. Which IC? The op-amp IC. So here we are calling that IC as a operational amplifier. Operational amplifier is basically multi-stage amplifier which uses the number of amplifier stages which are connected to each other in a complicated manner. So you will get the op-amp that we can use as a multi-stage amplifier. Only one girl is connected. Okay. Huh. So what we are saying here, when we are supposed to use multi-stage amplifier, at that time we can use that amplifier as a multi-stage if we are connecting number of amplifier interconnected to each other. At that time we can make multi-stage amplifier by using the number of op-amp. So here operational amplifier is having lots of advantages over the conventional amplifier. So what is meant by conventional amplifier? If we are making the amplifier by using the transistor, by using the coupling capacitor, bypass capacitor, biasing resistor, but instead of these things, only we are using the IC. At that time, if that IC is used for the differentiation purpose, for the integration purpose, for addition, subtraction, at that time we are saying that amplifier as a op-amp. So here it will have lots of advantages like it has smaller size, its cost is reduced because here we are using only one IC. It is highly reliable than the conventional amplifier. If you see about the power consumption, here we are connecting less number of components, due to which here power dissipation will be less. So we can say it will have less power consumption. It is easy to replace. Some op-amp we can use for the various application. It means what? We can use the same IC for the integration, for the differentiation, for the addition, for the subtraction. So we can say it will be the advantage of op-amp. Same op-amp we can use for the various multiple applications. If you see op-amp symbol, it will look like this. So basically, op-amp is a voltage amplifier with voltage gain. Voltage gain is nothing but it is the ratio of output voltage with respect to the input voltage. So here we can use the op-amp that can be used as a voltage amplifier with the higher voltage gain, that will be 2 into 10 raised to 5 or 10 raised to 6 dB. So here when we are using the IC, that we can be used as the op-amp. At that time, that IC will have the terminals like it. The IC will be the 8 terminal. So here at the pin number 2, we can give inverting, negative input. At pin number 3, we can give positive input. At the pin number 4 and 7, we can give the power supply. But here to the pin number 7, we can give positive. To the pin number 4, we can give negative power supply. At the pin number 6, we will get the output. So here, when we are using the op-amp, that we can be used as the differential amplifier. If here, if we see here, if we are using the op-amp, that is used to amplify the differential signal which is present between two input terminals. It means what? Here we are supposed to use the op-amp, but how? Here we are supposed to amplify the difference between the input signal. If we are having the two input signal V1 and V2, if we are connecting V1 to the positive terminal, non-inverting terminal, and if we are connecting V2 input to the negative inverting input terminal, at that time we can amplify V1 minus V2. So we can call that op-amp as a differential amplifier, and you will get VO equal to V1 minus V2. So here we are supposed to study about the differential input signal. So here it is nothing but it is the difference between the input signal, the positive input signal and the negative input signal. Or we can say it is the difference between non-inverting input signal and the inverting input signal, V1 and the V2. We can call that as a differential signal. We can take Vd equal to V1 minus V2. Now we are supposed to study the different parameters which we are supposed to use in the differential amplifier. You are supposed to calculate common mode signal. You are supposed to calculate differential gain, common mode gain, and total output voltage. So what does mean by the common mode signal? A common signal which we are giving to both input terminals. We are giving to the V1 and V2. At that time, we can call that signal as a common mode signal. If we are taking the two input signal and we are using that amplifier to amplify the difference between two input signals, at that time, the differential gain is nothing but it is the ratio of output voltage with respect to the difference between input voltage. So you will get AD, it is nothing but the differential, D for differential gain, equal to output voltage upon V1 minus V2, or you can take VD. This will be the difference between the input voltages. If you are calculating in the dB, you can calculate AD dB equal to 20 log 10, because this is the standard formula to take the dB value. If you are taking the dB here, you will get 20 log 10 in bracket VO upon VD. Now we are supposed to study about the common mode. It is nothing but when we are giving the common signal to both input terminal V1 and V2, at that time common mode gain will be defined as it is the ratio of output voltage with respect to the common mode voltage. And how will you calculate common mode voltage? Differential we will get by taking the difference. Common mode you will get V1 plus V2 upon 2. It means taking the average of both the input. So you will get Vc equal to V1 plus V2 by T. V1 plus V2 by 2. So you will calculate common mode gain AC equal to VO upon V1 plus V2 by 2. If you are calculating in dB, you can write AC dB equal to 20 log 10 in bracket VO upon V1 plus V2 by 2. Or you can write 2VO upon V1 plus V2. You can take that 2 in the numerator. Now, we are supposed to calculate the output voltage when we are taking the differential gain and when we are considering the common mode. At that time, you will get total output voltage, that is nothing but the output voltage, VO, equal to ADVD plus ACVC. It means what? Differential gain into differential voltage, plus common gain into the common mode signal voltage. It means what? You will get output voltage equal to ADVD plus ACVC. Now, we are supposed to study about the parameters which we are using in the differential amplifier like CMRR. You can call this as a common mode rejection ratio. I have drawn the same diagram. This is the same diagram. What we are doing here, we are giving one non-inverting input, inverting input. We are giving the power supply to the 4 and 7 pin number. We are taking here output. So here the common mode rejection ratio is defined as it is the ability of differential amplifier to reject the common mode signal. Mathematically, it can be calculated as it is the ratio of differential gain with respect to the common mode gain. So how will you calculate the differential gain? VO upon V1 minus V2. And what about AC? You can calculate VO upon V1 plus V2 by 2. So here VO will get cancelled and you will get CMRR equal to, AD upon AC. So you will get AD upon AC is nothing but you will get here V1 plus V2 upon V1 minus V2. So here we can denote CMRR by that rho. We can denote by this symbol, rho. So here we can say common mode rejection ratio. It is the ability of a differential amplifier to reject the common mode signal successfully. And we can call this as a figure of merit because it is calculating the gain of the differential amplifier as well as it is calculating the gain for the common mode. So you will get here ability of the amplifier to reject the common mode signal. So here we are supposed to study about some important characteristics of op-amp. If we are supposed to use op-amp as an ideal, at that time you will be required higher infinite voltage gain. Its input impedance or resistance will be infinite, but output resistance will be 0. Its offset voltage will be 0. But if you see in practice, op-amp, a small output voltage is present. Even through both input voltage V1 and V2 are having the 0 value, there will be some offset voltage. And we can call this as offset voltage, but for the ideal op-amp, we will require that offset voltage should be 0. Again, there is a concept of bandwidth. We will require the bandwidth value will be infinite. You can take bandwidth, it is nothing but it is the range of frequency over which all signal frequencies are amplified almost equally. So here we will require the bandwidth, that is nothing but the range of frequency over which all frequencies are amplified. You will be required infinite bandwidth for the ideal op-amp. Again, we are saying CMRR is nothing but it is the ratio of differential gain with respect to the common mode. So you will require infinite CMRR. you will require slew rate that will be also infinite. So what does mean by the slew rate? Slew rate is defined as it is the change in output voltage which will occur simultaneously with change in the input voltage. It means what? We can say the slew rate, it is the change in the input voltage which is occurring simultaneously with change in the input voltage. So you will require infinite slew rate. Now we are supposed to study about the power supply rejection ratio, PSRR. So you will be required there zero power supply. There will be question on the characteristics of ideal op-amp. That question come for the short answer or the question will come in the MCQs. Blank space, there will be the CMRR. It will be the infinite, it will be the finite, it will be the zero or the none of it. At that time, you are supposed to understand there will be the CMRR infinite, infinite slew rate. And here power supply rejection ratio will be 0 because power supply rejection ratio will specify the degree of dependence of op-amp output on the changes in the input supply voltage. And here we are supposed to maintain the constant output voltage. So we will not respect to change in the output voltage with respect to the change in supply voltage. So we can say we will require the 0 power supply rejection ratio because power supply rejection ratio we are defining as it is the degree of dependence of op-amp output on the change in power supply voltage. So you will get here PSRR will be equal to 0 voltage. Now we are supposed to study about the block diagram of op-amp. If you see, we are giving the op-amp input at the inverting and the non-inverting terminal. So here we can say the input stage that can be used as dual input balanced output differential amplifier. When we are giving the non-inverting and inverting terminal, at that time we are giving that input to the input stage where we are taking the dual input balanced output differential amplifier. After that, we are giving its output to the intermediate stage where we will get dual input, but there will be the unbalanced dual input unbalanced output differential amplifier. This output we are giving to the level shifting stage. Here we are supposed to shift the level. So we can use there any follower like emitter follower using the constant current source. Here we are supposed to shift the level. We have seen the emitter follower in our first section, first unit, the MOSFET analysis. So here again the output of level shifting we are supposed to give to the complementary symmetry push-pull amplifier. We have seen this concept also in our first unit. So here we are supposed to use at the output state the complementary symmetry push-pull amplifier. So here we are saying we can make op-amp by using input stage, by making output stage, intermediate and level shifting. At the input stage, we are using the dual input balanced output. So here when we are supposed to use op-amp at that time, input stage must satisfy the following requirement. It will have two input that will be inverting and the non-inverting. It must provide very high input impedance and it will give us low output impedance like a ideal op-amp. It must directly coupled amplify and must have infinite high CMRR. So we can say we can use here dual input balanced. We can use dual input balanced output differential amplifier. The output of input stage we are giving to the intermediate stage. So here the requirement of intermediate stage are as follows. It will require moderately high input and output resistance. First stage में हमने बोला था we will require higher input but output is low. But here we are saying we will require moderately high input and the output resistance also. Here we will require higher voltage gain. Here we can use dual input unbalanced differential amplifier and the output of intermediate stage we are supposed to give to the level shifting stage. So here, due to the direct coupling between the two stages, here we are supposed to use level shift. Here we are supposed to shift the level. So here, huh. So here, when we are using the level shifting stage at the output of intermediate stage, due to the direct coupling between the first two stages, because we have seen input stage and intermediate, there will be the direct coupling. So here, there is a direct coupling between the first two stages. The input of level shifting is amplified signal with some non-zero DC level. So here we can use the level shifting stage to bring that level to the 0 volt with respect to the ground. Then at the output, we are using the output stage after the level shifting stage, and the requirement for output stage will be, we will require low output resistance because we are supposed to amplify the signal. We will require larger output voltage. We will require larger current carrying capacity. So here we have seen the block diagram of the op-amp, which will consist of input stage, intermediate stage, level shifting stage, and the output stage. Now we are supposed to study about the op-amp, which will consist of the single IC, that will be the IC 741. This is the one of the oldest and the most popular operational amplifier integrated circuit. If you see, there are lots of features IC 741 is having, like it will have no frequency compensation required. There is a short circuit protection provided. There is a zero offset voltage capability. There will be no latch up. And if you see, there is a large common mode and differential voltage ranges. So these are the some features. If you see, IC 741 is a 8-pin IC. At the pin 1 and at pin 5, we can make this as a offset null. There is no need to make any connection. We can give inverting input negative at the pin number 2. We can give positive input at the non-inverting input, that is the pin number 3. We can give positive voltage supply at pin number 7. We can give negative supply at the pin number 4. We can take the output from pin number 6, and at the pin 8 there will be no connection. So here we can see the pin configuration of the IC741, which will have the 8 pin 1 and pin 5. This can be used to nullify the offset voltage because there we are taking null offset voltage. At the pin number 2 and pin number 3, we can take respectively inverting and the non-inverting input. At the pin number 4 and 7, we can give the power supply. At pin number 4, we can give negative power supply. And at the pin number 7, we can give positive power supply. Pin number 6, we will get the output from the pin number 6. And we are not connecting pin number 8 to any device. So we can say there will be no connection. This is the dummy pin. We are not using, and hence we can make that pin left open or the unconnected because we are not connecting anything. And here the specification, the features of the IC741 I have given for the idea what will be the value and the practically what are the value IC741 is having. If you see, it will have ideally infinite resistance, output resistance 0. It will have infinite bandwidth. It will have infinite gain. We are saying this concept. We are saying it will have the infinite CMRR. It will have infinite slew rate. It will have 0 PSRR. We are saying infinite offset voltage 0, but practically not possible. There will be the some value. So we have given here the specification for the IC 741. It will have some value of the input resistance. It will have, there is output resistance that will be equal to 75 ohm. It will have the CMRR in the dB, that will be the 90 dB. It will have the slew rate that will be 0.5 volt per microsecond. It will have the PSRR that will be the 150 microvolt per volt. If you see, IC741 is having lots of applications like it can be used as inverting and the non-inverting amplifier. We can use IC741 for the different applications like we can use as adder, we can use as subtractor, integrator, differentiator, circuit. We can use op-amp for other applications like voltage to current converter, current to voltage converter. We can use op-amp as anti-log, log amplifier. We can use op-amp as a precision rectifier. So these are the applications of the op-amp. Now we are supposed to study about the parameters like virtual short and virtual ground. Firstly, I will take your attention. If anyone is facing any issue, you can ask me. So here we are supposed to study about the virtual ground and the virtual short. As the name defines, what we are doing here, first we will see about the virtual short. If you see, we are using the same circuit here also for the IC7. Here we are taking the gain that is nothing but the differential gain equal to VO upon VD. VD means V1 minus V2. Now we are supposed to study about the virtual short and the virtual ground. So here firstly we will see about the virtual short. So according to the virtual short concept, both the input terminal are approximated at the same potential. It means what? There will be the no difference. So we will get the output voltage that will be equal to VO equal to gain into the differential input voltage. But what we are saying, if we are taking the virtual short at that time, both the input terminals are approximated at the same potential. So when we will see about the ideal op-amp, at that time, we will say we will get the voltage gain that will be infinite for the ideal. But if you see practically for the IC741, we will get the value for the voltage gain that will be 10 into 10 raised to 5. So here for the ideal op-amp, we are saying both input voltage will be zero. Both input voltage will be the same, approximately same. So you will get VD equal to V1 minus V2. You can write V1 minus V1 because both are having the same value. So you will get VD equal to 0. So we can say thus the potential difference between the input terminal is 0 because we are saying if we are making the virtual short, you can see here when we are doing here virtually short, both will have the same voltage. We are connecting this with each other, so both will shorted. So here there will be the no amount of voltage because we are taking both as the same. So differential input voltage will become zero. So we can say according to the virtual short concept, if both terminals are approximated at the same potential voltage at that time, you will get the difference between input terminal is zero. Now we are supposed to study about the virtual. If the non-inverting terminal is connected to the ground, it means what? Positive terminal. Then due to the virtual short exists between two terminals, inverting will also act as a ground. What we are doing here, when we are supposed to study about the virtual ground concept at that time, if non-inverting terminal, that is nothing but the positive terminal, we are connecting with the ground. If we are connecting positive terminal with the ground, at that time we can say due to the virtual short existing between the input terminal, because we are connecting input terminal, we are shorting and we are connecting our नॉन इन्वर्टिंग टर्मिनल टू द ग्राउंड एंड इनपुट को जो है शॉर्ट किया है, ड्यू टू विच इन्वर्टिंग also will work as a ground. क्या है? If we are using this circuit diagram, we are doing input terminal shorting. We are shorting the both input terminal, inverting and non-inverting, and we are grounding the positive terminal, non-inverting. At that time, negative terminal, inverting terminal will also behave as a ground terminal. This concept we are saying as a virtual ground because inverting terminal will also behave as a ground terminal. So hence we can say that as a virtual ground. Now we are supposed to study about the configuration of the op-amp. So we can use the op-amp in the different two modes. We can use the op-amp in the open loop mode, or we can use the op-amp that will be in the closed loop. So open loop means what? The open loop configuration is that there is absolutely no feedback. If we are not connecting output again to the input, we can say that circuit will behave as an open loop because here is no feedback from output to the input. And if we are saying about the closed loop, at that time, in a closed loop configuration, we are supposed to return back to the input. It means what? Here we are supposed to take a part of output which will be returned back as a feedback to the input. So there will be the loop exists. So in the closed loop configuration, again we are having the two types. We can give that output as a feedback to the inverting terminal or to the non-inverting circuit. So depending on the type of feedback, we are having two types of feedback configuration for the closed loop configuration. These are nothing but the regenerative feedback, or we can say as a positive feedback. And another type will be the degenerative feedback, or we can say it will be working as a negative feedback amplifier. So here we are supposed to see how will be the positive and how will be the negative feedback. So here, if we are connecting the feedback signal, that is, if we are returning back from output, we are taking the part of output, returning back to the input. At that time, if feedback signal, the output signal, original signal is in phase with the other signal, that time we can say that as a positive feedback. If you see, we are we have seen in the third unit, that is nothing but the oscillator. Voltage regulator mein humne last mein we have seen the oscillator. So we have seen oscillator is using the positive feedback. If you see, Smith trigger, it also uses the positive feedback. So you can take applications as oscillator or the Smith trigger because they are taking the positive feedback. And if you are talking about the negative feedback, when we are returning back from output to the input, at that time, if the signal which is fed back to the input and original input signal, means feedback signal and original input signal, both are out of phase, both are out of phase of 180 degree, at that time you can say that type as a negative feedback amplifier. Here we can say this type of amplifier as a negative feedback because if you see the output signal, it means what? The feedback signal and the original input signal जो यहाँ पे है और जो output से आ रहा है, both will have 180 degree out of phase. So we can say that type of feedback as a negative feedback. And if you see the applications, you can take application as a amplifier because amplifier is taking the negative feedback. Amplifier is using the negative feedback. So you can take as a application as the amplifier for the negative feedback amplifier. Now we are supposed to study about the closed loop because if you see closed loop configuration, we are having the two types, negative inverting and the non-inverting. This is nothing but the positive. So here we are supposed to study about the op-amp configuration, which will have different types like inverting amplifier, adder, subtractor, non-inverting, integrator, voltage follower, differentiator, instrumentation amplifier. All these amplifier configuration we are supposed to study in our syllabus. There will be question on voltage follower, there will be question on instrumentation amplifier because all these things they are given in our syllabus. If anyone is facing any issue, you can ask me. Now I am taking your attendance. Okay. In our today's syllabus, we have seen about the operational amplifier in which we have seen the different parameters. We have seen parameters like the common mode rejection ratio, differential amplifier, slew rate, power supply rejection ratio. We have seen about the virtual short and virtual ground concept. We have seen IC741, which is having different features for the ideal IC741. We have seen the block diagram of op-amp. So when we are supposed to use op-amp as ideal, at that time we will require infinite voltage gain, infinite input resistance, zero output resistance, zero offset voltage, infinite bandwidth, infinite CMRR, infinite slew rate. Infinite slew rate is nothing but slew rate is defined as it is the change in output which is occurring simultaneously with change in the input. If output input it changes, we are supposed to change the output also. So we will require for the ideal op-amp infinite slew rate. We can denote slew rate by letter S. Then we have seen about the CMRR. It is nothing but we can call CMRR as the common mode rejection ratio. It is the ability of a differential amplifier to reject the common mode signal. And how will you get? We can mathematically calculate common mode rejection ratio. It will be the ratio of differential gain with respect to the common mode gain. And we can denote CMRR by letter rho. This is the symbol. We can denote CMRR by this. If you see here, when we are using the op-amp, that will be the IC741. If we are giving the two input, at that time, we can calculate the differential gain from positive, non-inverting to the negative. It means what? V1 minus V2. And when we are supposed to calculate the common mode gain, you can take the common mode. It means what? If we are giving the input V1 and V2 and we are connecting this, we are shorting this. At that time, you can take V1 plus V2 by 2. Average of that input terminal, we can take as a common mode. So here you can calculate CMRR equal to AD upon AC. Now there will be the zero power supply rejection ratio. So power supply rejection ratio is defined as it will specify the degree of dependence of op-amp on the changes in the supply voltage. So we are supposed to maintain the output constant irrespective in the changes in the supply voltage. So we can say we will require zero power supply rejection ratio. Block diagram of op-amp will consist of four stage: input stage, intermediate stage, level shifting stage, output stage. At the input stage, we can use DL input balanced differential amplifier. And the output of input stage we can give to the intermediate where we are using the DL input but unbalanced differential amplifier where we will require moderately high input and the output resistance, and we will require higher voltage gain. The output of intermediate stage we can give to the level shifting stage. Here we are supposed to change the level. We are supposed to shift the level. So due to the direct coupling between the first two stages, input stage and the input intermediate stage, the input of the level shifting stage is the amplifier. So here we are supposed to use level shifting stage to bring this DC level to the 0 with respect to the clock. And the output of level shifting stage we can give to the output stage where we will require low output resistance and larger output voltage swing. If you see, we are using the IC741 which is having lots of advantages specification, like we will require there will be the offset voltage at the pin. If you see, at the pin 1 and at the pin 5, we are taking the offset null voltage. Again, we are using the IC741 which is having the 8 pin IC. We have given here the pin configuration. We can give the input at the pin 2 and 3 and we can take the output at the pin number 6. We will give the power supply, positive power supply at pin number 7, negative power supply at the pin number 4. These are specifications for the ideal IC741 and the practical IC741. It It is having lots of applications like we can use IC741 as adder, subtractor, integrator, differentiator. Now we are supposed to study about the virtual short and virtual grounds concept. So virtual short means what? If we are giving the input at the inverting and the non-inverting terminal, and if we are taking input terminals are approximately having the same potential value. If we are taking V1 equal to V2 equal to V, all are having the same value according to the virtual short concept. So you will get the output voltage will be equal to AV into VD. But here we are taking VD equal to 0. So you will get here output voltage that will be, here you will get, if you are taking the virtual short concept, you will get both input voltage will be same, so you will get VD equal to 0. So for the ideal op amp, potential difference between input terminal we are taking as a 0. And if we are connecting non-inverting terminal, positive terminal to the ground, and if we are making the virtual short at the two input terminal of the op amp, at that time its inverting terminal will also work as a ground potential. So we can say this concept as a virtual ground. There is an electricity issue. Just wait for a minute. My voice is coming. There was a network issue. Voice आ रहा है अभी? Am I audible? Okay. So what we are saying here, when we are connecting non-inverting terminal of op amp to the ground, and as there is a virtual short in between the two input terminals, at that time its inverting terminal will also behave as a ground. So we can say that as a virtual ground. We can take op amp in the two configuration like open loop mode and the closed loop. If we are not taking the feedback from output to the input, we can say that as a open. And if we are taking the output, that will be written back as a feedback to the input. We can say that as a closed loop configuration, and we can take closed loop configuration in two ways. The positive feedback, or we can say the regenerative feedback loop configuration, and another negative, or we can say degenerative feedback closed loop configuration. So here we can see we can use that op amp in the closed loop configuration for positive and the negative feedback. If we are giving the positive, that is nothing but the output signal as a feedback to the input, and if both the feedback signal and original input signal are in phase, at that time we can say that as a positive feedback. We can take example as oscillator or the Smith trigger. And if we are taking the feedback back from output to the input, but here the input signal and the feedback signal are 180-degree out of phase. At that time, we can say that type of amplifier as a negative feedback amplifier. If you see here, we are connecting the output to the input and it is 180-degree phase shift. We are giving to the inverting terminal. So here output, when we are giving as a feedback and the original input, both will be in the 180-degree out of phase. So we can say that as a negative feedback, and here we can take as example as a amplifier. So here we are supposed to study about the op amp configuration that will be having the closed loop configuration. So in our syllabus we are having the lots of closed loop op amp amplifier configuration like inverting amplifier, adder, subtractor, non-inverting amplifier, integrator, voltage follower, differentiator, instrumentation. We will see one by one in the next session. If anyone is facing any issue, you can ask me. Otherwise, you guys can leave now. We will conclude our session. Okay, thank you.